Welcome to the Power Electronics class. Myself B. Veernarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. We are in second unit of this Power Electronics, AC to DC converters. Up to now, we completed the single phase half wave controlled converters with different types of loads, R, RL and RLE loads, and single phase full wave converters. Depends upon the configuration. Full wave controlled converters are classified into two types, like midpoint type fully controlled converters and bridge type full wave converters. We already completed the midpoint type full wave controlled converters with R, RL and RLE loads, and we discussed this single phase bridge type full wave controlled converters with R and RL loads and RLE loads also. Depends upon the circuit inductance, load inductance value. The fully controlled converters maybe operates in two modes, either rectification mode or inversion mode. Now we go through this single phase semi converter or half controlled converter single phase semi converter or half controlled converter with R load. Why you need these semi converters or half controlled converters? Previously we concentrate on single phase bridge type fully controlled converters. We have some advantages of these bridge type fully controlled converters over midpoint type full wave converters. And if you go through these bridge type fully controlled converters, those are preferred at a time if you want to collect the two quadrant operation. Two quadrant operation means if both output voltage and output currents are positive, then that is said to be first quadrant operation, which is rectification is possible. And here alpha is less than 90 degrees. And if you go through these alpha greater than 90 degrees, and here we are getting fourth quadrant operation. So at a time, if you want to collect the two quadrant operations from the single converter, that is either first quadrant operation or fourth quadrant operation, depends upon the load requirement, then we will go through the fully controlled converters, like bridge type fully controlled converters. I just want to collect only first quadrant operation, that is always the output voltage and output currents are positive for the entire firing angle range from 0 to 180 degrees. I just want to collect the first quadrant operation. Simply we go through the semi converters. So semi converters are half controlled converters. These semi converters further classified into two types, depends upon the circuit configuration. Those are symmetrical semi converters and asymmetrical semi converters. First we go through the symmetrical semi converters. Most of the switching applications, simply we go through the symmetrical semi converters. Now we will construct the single phase symmetrical semi converter with R load. Coming to the circuit diagram. Coming to this one is the single phase symmetrical semi-converter. If you go through the bridge type fully controlled converters, it consisting 4 ideal SCRs. Assume ideal switches, it consisting 4 SCRs. If you go through the semi-converter or half controlled converters, it consisting 2 controllable devices and 2 uncontrollable devices. Here the 2 controllable devices are 2 SCRs and 2 uncontrollable devices are 2 diodes. So the circuit diagram of this semi-converter or half controlled converter consisting total 4 devices. Out of these 4, 2 are controllable devices and 2 are uncontrollable devices. So it consisting 2 SCRs and 2 diodes. Depends upon the circuit configuration or arrangement, these semi-converters are classified into 2 types. Those are symmetrical semi-converters and asymmetrical semi-converters. If you go through the circuit diagram, if you keep one SCR and one diode on one leg, another thyristor, another diode keep another leg, then this is simply consisting the symmetrical semi-converter. Or if you keep 2 SCRs on one leg, 2 diodes on another leg, those are simply considered as the asymmetrical semi-converters. So most of the switching applications, simply we go through the symmetrical semi-converters. So we concentrate on the symmetrical semi-converter. Here I just want to explain the operation of single phase semi-converter or half control converter with R load. So simply the circuit diagram consisting one isolation transformer. Here we have the primary winding voltage Vp is equals to Vm sin omega t. Isolation transformer simply used to isolate or separate the source and these power electronic switches. So here I am taking 1:1 transformer now, hence why the secondary winding voltage is also equals to Vm sin omega t, and it consisting 2 ideal thyristors and 2 ideal diodes and resistive load. That is a simple circuit description of single phase semi converter. So single phase semi converter simply consisting one isolation transformer and 2 ideal SCRs, 2 ideal diodes and resistive load. Coming to this operation, during the positive half cycle of the supply, here it is VAB and it is VBA. So during the positive half cycle of the supply, here terminal A is positive and B is negative. Terminal A is positive and B is negative. Corresponding that T1 anode is connected to the positive terminal now, so T1 comes to the forward biasing mode. T2 anode connected to the negative terminal, so T2 goes to the reverse biasing mode. D1 cathode connected to the negative terminal, so D1 comes to the forward biasing mode. D2's cathode connected to the positive terminal, so D2 goes to the reverse biasing mode. So during the positive half cycle of the supply, terminal A is positive and B is negative, corresponding that T1, D1 are in forward bias, T2, D2 are in reverse bias. If both the switches are in the on state, then the source is transmitted to the load. Here from 0 to pi or during the positive half cycle, T1 is forward bias. It is also off state of the SCR. So the switch is till it is in open position. D1 is forward bias. You go through the ideal diode now. So as long as the diode is coming present in the forward bias, it is simply in the on state. So even though D1 is in the on state, it is uncontrollable device. If you made cathode is negative and anode is positive, by default it comes to the forward bias. If you go through the ideal diode, that forward bias condition is considered as the on state of the diode and reverse bias is considered as the off state of the diode. So from 0 to pi, even though T1 comes to the forward bias, D1 is already in the on state, the source is transmitted to the load. So at omega t is equals to alpha, we provide the gate pulse to the first thyristor. Here why should I mention IC1 only means D1 is uncontrollable device. Thyristor 1 is the controllable device. So if the thyristor is in forward bias, if you provide the gate pulse, then it comes to the on state. So at omega t is equal to alpha, we provide the control signal to the T1. So from this alpha to pi, already T1 is in forward bias. So from alpha to pi, the source voltage VAB is transmitted to the load, and current flow through the circuit is from this A plus, T1, R, D1, B minus, and the secondary winding of the transformer, and like this. So the current flow through the circuit will be circulates in this path. So corresponding that the VAB is available across the load. So the output voltage simply follows the VAB curve from this alpha to pi. So what you are getting here, from alpha to pi, here it is the output voltage. And if we go through the output current, output current here we have the resistive load, hence why I naught is equals to simply V naught by R. Hence why from alpha to pi, this is the output voltage. Next, at omega t is equal to pi, both the output voltage 0 and output current is 0, and after that the negative half cycle will be available, corresponding the T1, D1 are in reverse bias. And during the negative half cycle of the source, from pi to 2 pi, what happens here? From pi to 2 pi, during the negative half cycle, so during this negative half cycle, terminal A is negative and B is positive. During this negative half cycle, terminal A is negative and B is positive. Corresponding that T2, D2 are in forward bias, T1, D1 are in reverse bias. At omega t is equals to pi plus alpha, we provide the gate pulse to the second thyristor, hence why we can mention here Ig2. Due to that, from pi plus alpha to 2 pi, T2, D2 are in the on state. If T2, D2 are in the on state, VBA simply available across the load. Hence why the output voltage simply follows the VBA curve, this one. So from pi plus alpha to 2 pi, and this is alpha to pi, and here from pi plus alpha to 2 pi, if you go through this output current, simply it is in phase with respect to the voltage. Why? Because here we have the purely resistive load, hence why the current is always in phase with the voltage. So here from alpha to pi, T1, D1 are in the on state, from pi plus alpha to 2 pi, T2, D2 are in the on state. And again same, positive half cycle, we provide the gate pulse to the T1, D1, and here we provide the gate pulse to the second thyristor. So T2, D2 are in the on state, and corresponding the current waveforms are like this. Here this is for simply single phase semi converter with R load. And coming to the average DC output voltage here, V0 is equals to how many pulses you are generated here for completion of one full cycle? 2 pulses. So 2 by 2 pi integral, what is the duration of the pulse? Alpha to pi. How much voltage you transfer? Vm sin omega t d omega t. Very simple. So by simplifying this expression, V naught is equals to Vm by pi. Integral sin omega t is minus cos omega t between the limits alpha to phi. So finally V naught equals to Vm by pi into 1 plus cos alpha. This is a simple average DC output voltage for single phase semi converter or half controlled converter with R load. If you want to find out the RMS output voltage, na simple, Vrms is equals to same 2 by 2 pi integral alpha to pi Vm square sin square omega t d omega t whole power 1 by 2. So already we simplify this expression. If you simplify this expression, you are getting the RMS output voltage. Like bridge type full wave converters with R load, the same performance is observed here. So this is a simple representation of single phase semi converter or half controlled converter with R load. Next we concentrate on this single phase semi converter with RL load. So we go through this next one. Single phase semi converter with RL load. So coming to the circuit diagram, it is the L and it is the R, and simply it consisting RL load. So here single phase semi converter with RL load, circuit diagram is same. It consisting one isolation transformer, two ideal thyristors and two ideal diodes, but the load should be considered as here RL. That means the series combination of resistor and inductor should be considered as the load for these half controlled converters. And if you go through this operation, what you observe here, yeah, right. Yes, if you go through the operation of this semi converter with RL load, same during the positive half cycle of the supply, here terminal A is positive and B is negative, corresponding that T1 comes to the forward biasing mode and D1 is in forward biasing mode, T2, D2 are in reverse biasing mode. At omega t is equal to alpha, we provide the gate pulse to the first thyristor, so T1 comes to the on state. So from alpha to pi, output voltage simply follows the VAB and the current flow through the circuit is A plus T1 R L D1 B minus and secondary winding of the transformer. So during this path from alpha to pi, due to the conduction of T1 D1, there was some energy must be stored in the inductor. There was some energy must be stored in the inductor. So here what observe here, from alpha to pi, output voltage simply follows the VAB, hence why the output voltage simply like this, no problem. But coming to the current, due to the presence of the inductor, assume continuous conduction mode, that is if you have large value of the inductor, then from alpha to pi, the energy stores in the inductor should be charging. So hence why the current should be increases exponentially like this. So from alpha to pi, some energy must be stored in the inductor. Here I am assuming continuous conduction mode. That means large value of the inductor should be present in the load side. Hence why we are getting the continuous conduction mode. So observe here, at omega t is equals to pi, even though output voltage 0, output current cannot be 0. Output current cannot be 0. Then what happens? The energy stores in the inductor is discharges. So how that energy stores in the inductor should be discharged here? See, after pi, the negative half cycle will be available across the load or across the thyristors. During that negative half cycle, what observe here? Terminal A is negative and B is positive from pi to 2 pi. So D1 goes to the reverse biasing mode, T2 comes to the forward biasing mode, D2 is in forward bias, that means on state. Actually from alpha to pi, there was some energy must be stored in the inductor. Then the energy stored in the inductor is try to discharge through this D2, T1 and load. Actually from alpha to pi, due to the conduction of T1, D1, some energy is transmitted from source to the load. Corresponding that there was some energy must be stored in the inductor. After pi, the D1 goes to the reverse biasing mode, hence why the discharging current should not pass through the D1. Why? Because it is in reverse bias, off state. And it will set T2, T2 is in forward bias, off state. Hence why that discharging current is done through the D2. Why? Because D2 is already in forward bias during the negative half cycle. Why? Because anode is connected to the positive terminal and cathode connected to the negative terminal. So D2 comes to the on state. And due to this energy stores in the inductor discharges to the T1, T1 is continuously maintain its on state up to the instant where the next incoming SCR is present. Hence why we clearly observe from pi to pi plus alpha, the energy stores in the inductor is discharges due to the conduction of T1 D2. Due to the conduction of T1 D2, the energy stores in the inductor is discharges. But from alpha to pi, due to the conduction of T1 D1, the energy stores in the inductor will be taken place. Here very important, the energy stores in the inductor is discharges through T1 D2. And at omega t is equal to pi plus alpha, we provide the gate pulse to the T2, hence T1 goes to the off state and T2 comes to the on state. So at omega t is equal to pi plus alpha, T2 is the incoming SCR and T1 is the outgoing SCR. And from pi plus alpha to 2 pi, T2, D2 are in the on state. So if T2, D2 are in the on state, what is the current flow through the circuit? Here, if T2, D2 are in the on state, the current flow through the circuit is represented by through this path B plus T2 R L D2 A minus secondary winding of the transformer and B plus. Through this path, the current will be flow through the circuit. Again, there was some energy must be stored in the inductor. See here, if you go through the current waveform, again the current should be rising in nature due to the conduction of T2, D2. Similarly, here also at 2 pi, even though the output voltage 0, output current cannot be 0, hence why the energy stores in the inductor is discharges through the D1. Through the D1. So what happens here? During this negative half cycle, there was some energy must be stored in the inductor. So that energy stores in the inductor is discharges through D1, T2 and resistive load. So here the discharging path is taken through the T2, D1. So simply acts as the short circuit across the load. So what is the voltage across the short circuit? 0. Hence why here the output voltage is 0, but you have some output current which is collected due to the conduction of T2 D1. which is collects through the conduction of T to D1. And similarly, rising current due to the conduction of T1 D1 and discharging T1 D2 and T2 D1. In this way, we are collecting the output voltage and output current waveform. So similarly, here also discharging path. Okay. Here also T2 D1 will be in the on state. And see here, where the energy stores in the inductor is discharges, then the output voltage is 0. That means even though you have the load inductor, we are unable to collect the negative pulses in the output voltage waveform. Whereas in fully controlled converters in the bridge type, due to the presence of the inductor in the load side, we are collecting the negative pulses in the output voltage waveform. Negative pulses means there was some energy must be transmitted from load to the source. But in these semi converters, there is no possibility of the inversion. That means there is no energy is transmitted from load to the source. The energy stores in the inductor is again fed back to the load through this T1 D2 or T2 D1. Or in sometimes you can represent here freewheeling diode. If you represent the freewheeling diode here, what happens? If you have the freewheeling diode here, then the energy stores in the inductor is discharges through the freewheeling diode. Then there is no function of this T1 D2 or T2 D1. Those are replaced by the freewheeling diode. In this portion, if you have the freewheeling diode, this portion is simply eliminated. Instead of this, here you have the freewheeling diode. The freewheeling diode is coming to the picture. So, if you go through this semi-converter with RL load, again you have the same output voltage. V0 is equals to, for completion of one full cycle, written 2 by 2 pi. Integral limitations are alpha to pi. And average DC output voltage is V0 is equals to Vm by pi into 1 plus cos alpha. Here it is for RL load and in continuous conduction mode. So what you observe here? If alpha equals to 0, what is V0? 2 Vm by pi. Cos 0 is 1, 1 plus 1 2, so 2 Vm by pi. If alpha equals to 90, what is the V0? Cos 90, 0, then output voltage is Vm by pi. If alpha equals to 180, what is the V0? Cos 180, minus 1, minus 1 plus 1 gets cancelled, so final output voltage is 0. So if you go through this semi-converter, what you observe here, for the entire firing angle range, always the output voltage is positive. If alpha is 0, we are getting the maximum output voltage, which is 2 Vm by pi. If alpha equal to 180, then output voltage is 0. So for the entire firing angle range, always the output voltage is positive and output current is positive. So only we are able to collect the rectification. That is, first quadrant operation is able to collect from the semi-converter. This is the main advantage of the semi-converter or half controlled converter. If you go through the fully controlled converter now, depends upon the firing angle under RL loads or RLE loads. If alpha less than 90 degrees, we are able to collect the rectification operation, that is first quadrant. If alpha greater than 90 degrees, we are able to collect the inversion operation, that is fourth quadrant operation. So at a time, if you want to collect the two quadrant operation, simply we prefer the fully controlled converters, bridge type fully controlled converters. Or I just want to collect the single quadrant operation for the entire firing angle range, then simply we go through these semi-converters or half controlled converters. So here this is the simple representation of single phase semi-converter or half controlled converter with RL load. And if we go through the RLE load, in continuous conduction mode, there is no effect of the back EMF. We are getting the same performance. If you go through the discontinuous conduction mode, then the back EMF is coming to the picture. In discontinuous conduction mode, what you observe? For example, for the same half control converter, if I am go with the RLE load, then we will see how that waveform should be varies. RLE load. Then the circuit diagram can be redrawn like R, L and E, back EMF. And if you go through the continuous conduction mode, there is no effect of the back EMF. You are getting the same output voltage, output current and same performance parameters. But if you go through the discontinuous conduction mode, then this current waveform and the voltage waveform can be changed like here current should be charges and discharges. Here it is the off, and again charges, discharges, and this is the 0. Charges, discharges, here it is the 0. Charges, like that. So similarly here also like this. So like this. So if you go through the RLE loads in discontinuous conduction mode, from pi to beta, the conduction of T1 D2 is present, and beta to pi plus alpha, all the devices are in off state. If all the devices are in the off state, in that portion the back EMF is coming to the picture. So here the output voltage is equals to the E. Here the output voltage equals to the E. And here again discharges 0. Again here you have the output voltage like this. So here this is the magnitude of back EMF. So where all the devices are in the off state and the output current is 0, in that portion the back EMF is coming to the picture. That is a simple representation of RLE load under a discontinuous conduction mode. If you go through the continuous conduction mode, then there is no effect of the back EMF. Here these are the representation of single phase semi converter with the different types of loads, R load, RL load and RLE loads. RL load with freewheeling diode. If you consider the freewheeling diode, here the function of this T1 D2 is simply replaced by the freewheeling diode. And here also, here you have T2 D1. If you have the freewheeling diode, instead of T2 D1, simply the freewheeling diode is coming to the picture. The freewheeling diode is always connects across the load. So here this is a simple representation of half controlled converter or semi converter with R, RL and RLE loads. This is the average DC output voltage, V naught equals to Vm by pi into 1 plus cos alpha. Whereas if you go through the bridge type fully controlled converter, what you are getting, V naught is equals to 2 Vm by pi cos alpha. So from this, if alpha is 0, V naught equal to 2 Vm by pi. If alpha equal to 90, V naught equal to 0. If alpha equal to 180, V naught equal to minus 2 Vm by pi. So depends upon the firing angle, we are able to collect either positive voltage or negative voltage. If the positive voltage is present, rectification operation. If the negative voltage means some power should be transmitted from load to the source, hence why the inversion operation should be taken place. So now we conclude that if we go through the fully controlled converters, we are able to collect 2 quadrant operation at a time. If you go through the semi converters or half controlled converters, we are able to collect the single quadrant operation for the entire firing angle range. Now we concentrate on three-phase converters. So up to now we are discussing in classification of the converters. We already discussed the starting of the second unit. Classification of the converters depends upon the voltage or depends upon the source availability. The controlled converters or AC to DC converters are mainly classified into two types: single phase converters, three phase converters. Now we completed the single phase converters like single phase half wave converter, single phase full wave converters. In single phase full wave converters we concentrate on bridge type converters and midpoint type converters. Again, bridge type converters are classified into two types like fully controlled converters and half controlled converters. We discuss all these topics. Now we concentrate on three phase controlled converters. What is the need of the three phase controlled converters? As already said, if you have the more number of pulses in the output voltage of the converter, then the harmonic frequencies, the fundamental harmonic frequencies are more. The order of the harmonics are high if you have more number of pulses in the output voltage. So those higher order harmonics can be easily eliminated by using the low rating filters. If you go through the single phase converters, if you go through the half wave converter, we are able to collect only single pulse. If you go through the full wave converters, we are able to collect the two pulses. So if you go through the three phase converters, the number of pulses in the output voltage may be increases, either 3 pulses or 6 pulses, depends upon the circuit configuration or circuit arrangement. We are able to collect either 6 pulse or 3 pulse or 12 pulse, like that. So these three phase converters are preferred for high power applications. If the load requirement is greater than 15 kilowatts, then to fulfill that load demand, simply we go through the three phase controlled converters. If the output power rating is less than 15 kilowatts, then the single phase controlled converters are sufficient to fulfill the load requirements. If you go through the high power ratings, like if you want to fulfill the load demand above the 15 kilowatts, then simply we go through the three phase controlled converters. Here the three phase controlled converters are also classified into two types like three phase half wave converters and three phase full wave converters. First we concentrate on three phase half wave converters. So what is the need of the three phase converters? Means to fulfill the high power demands, and if the power rating is greater than the 15 kilowatts, to fulfill the load demand, simply we go through the three phase converters. If you go through these three phase converters, we are able to improve the number of pulses in the output voltage. So we are getting the better DC output voltage than single phase converters, and the order of the frequencies is high. That means the order of the harmonics is high. Hence why the higher order harmonics can be easily eliminated by using the low filters. Hence why simply we concentrate on three phase converters. So first we go through this three phase half wave controlled converter with R load. Three phase half wave controlled converter with R load. Coming to the circuit diagram, So if you go through the representation of three-phase voltages, take one horizontal line as the reference. Above the reference line and below the reference line you draw two dotted lines like this, and you divide first one 30 degrees, next you double, this is 90, 150, 210, 270, 330, 390. Next you start from here and you cross, and similarly like this, like this. After that you join the alternative peaks, this one, this one. Similarly alternative peaks like this. So if you go through this first one 0 to 180, here this is the representation of VA0 and this is the representation of VB0 and here it is the representation of VC0. So what is the phase difference between the two phases? 120 degrees. So observe here, if the phase A is originates at 0, after 120 phase B is originated. After 120 at 240 phase C. So that is the representation of three-phase voltages. So coming to this three-phase half-wave control converter with R load, the circuit consisting one three-phase transformer whose primary winding is connected in delta fashion, which is connected to the source, and the secondary winding is connected in star fashion, and it consisting three ideal SCRs which are numbered as T1, T2, T3. T1, T2, T3 and resistive load. Here the resistive load is connected between common cathodes of these three thyristors. Common cathodes means this point. Here this is the cathode and this is the cathode and this is the cathode. The common point of these three SCRs to the neutral point of the star connected secondary winding of the transformer. What is the neutral point here? This one. So between these common cathodes of the thyristors to the neutral point, we will connect the resistive load like this. Here we have the R0, R resistive load and output voltage and output current. So coming to this operation, here we have the three thyristors. So which thyristor is coming to the forward biasing mode and which is the reverse biasing mode, that should depends upon the source voltage. That should depends upon the source voltage. See here we have the three phase voltages VA, VB, VC. We consider VA0, VB0, VC0. So out of these three phases, which is more positive, corresponding thyristor comes to the forward biasing. At any instant, out of these three phases, which is more positive, corresponding thyristor comes to the forward biasing mode. Here we have the three phases now, phase A, phase B, phase C. Phase A is given to the first thyristor, phase B given to the second thyristor and phase C given to the third thyristor. So here, see, from 30 to 150, from 30 to 150, here from 30 to 150, which is more positive? This one. Phase A is more positive from 30 to 150. So from 30 onwards, T1 comes to the forward biasing. So from 30 to 150, T1 is in forward bias. So here from omega t is equals to 30 to 150, T1 is in forward bias. Remaining T2, T3 are in reverse bias. Next, from 150 to 270, which is more positive? Phase B. Phase B is more positive. So from this 150 onwards, T2 is in forward bias. So from this 150 to 270, T2 is in forward bias. T2 is in forward bias. from 270 to 390, which is more positive? Phase C. What is the thyristor connects to the phase C? T3. So from this 270 to 390, T3 is in forward bias. Before this also T3. So T1, T2, T3. Next T1, T2, T3. That is the cycle. So observe here, between 30 to 150, if you provide the gate pulse, then T1 comes to the on state. If you provide the gate pulse to the T1 before 30, it is not coming to the on state. Why? Because phase C is more positive, hence why T3 is in forward bias, corresponding that T1, T2 are in reverse bias. So where the thyristor comes to the forward biasing, in that forward biasing condition only, if you provide the gate pulse, corresponding thyristor comes to the on state. So here we are able to trigger the T1 between 30 to 150 only, and we are able to trigger the T2 between 150 to 270 only. If you want to trigger the T3, it is possible between 270 to 390 or between 0 to 30 only. So here what I am said, if you choose alpha is equals to 0, if you choose alpha is equals to 0, then where the T1 comes to the on state? From T1 is on from 30 to 150. Why? Because even though you consider alpha 0, T1 comes to the forward biasing at omega t is equal to 30. Hence why you add that 30 degrees by default. Then it is easy to draw the output voltage waveforms for different types of the firing angles. So if alpha equal to 0, T1 on at 30 to 150, and similarly T2 is on at 150 to 270, T3 is on at 270 to 390 and 0 to 30. So if I just want to draw the output voltage waveform, here I just want to draw the output voltage waveform for alpha equal to 0. How we will write? 30, 150, 270, 390. Mark that one. 30, 150, 270, 390. So what you are getting here? From 0 to 30, T3 is on. If T3 is on, then output voltage V0 is equals to Vc0. If T2 is on, then output voltage equals to Vb0. If T1 is on, then V0 is equals to Va0. Why? Because see here, if T1 is in the on state, then the current flow through the circuit is like this. If T2 is on state, current flow through the circuit is like this. If T3 is in the on state, in this way the current will be flow through the circuit. So you blindly follow from 0 to 30, Vc0 na, this portion. 0 to 30, 30 to 150, 150 to 270, then output voltage simply are getting like this. That is the output voltage waveform for alpha equal to 30. If you want to draw the output voltage waveform for alpha equal to 30 degrees, for example, just tell me how you draw the output voltage waveform for alpha equal to 30. Here I just want to try to draw the output voltage waveform for alpha equal to 30 degrees. So if you take alpha equal to 30 degrees, where the T1 is in the on state, as already said, we have 30 degrees by default. Why? Because if you choose previous case alpha equal to 0, T1 on at 30. So if you take alpha equal to 30, where the T1 comes to on state, 30 plus 30, 60 degrees. So from 60 to 180. The conduction portion of each SCR is 120 degrees. The conduction period of each SCR is 120 degrees. So 60 to 180. Corresponding that T2, 180 to 300. T3, 300 to 420. And 0 to 60. So here V0 is equals to VA0. Here V0 is equals to VB0. Here V0 is equals to VC0. So I just want to draw the output voltage waveform for alpha equal to 30. Then 0 to 60 VC0. Where is that waveform? See. 0 to 60 VC0. This one. 60 to 180 VA0. Then you follow VA0. 60 to 180. Next 180 to 300 VB0. VC0. Then you are getting the output voltage waveform. This 0 to 60 na. This one 60. This one 180. This one 300. 420. It is 420. Then your output voltage waveform is like this. Like this. Like this. This is the output voltage waveform for alpha equal to 30 degrees. You mentioned conduction portion of each SCR. It is T1, it is T2, here it is T3, and here also T3. Here it is T3, it is T1, it is T2, it is T3. Here for completion of one full cycle, how many pulses you have generated? This is one pulse, this is the second pulse, and 0 to 60 and 300 to 360. Here half pulse and here half pulse. 360 degrees now. Where is 360? This one. 360. Here it is half and the remaining half is here. So for completion of one full cycle, we are able to producing the 3 pulses in the output voltage waveform. Hence why this 3-phase half wave converter is called the 3-pulse converter. 3-phase half wave converter is called the 3-pulse converter. So these are the output voltage waveform for alpha equal to 30. Next we will draw another one for alpha equal to 60. Then you understand the difference. Alpha equals to 60. So draw the timing diagram for alpha equal to 60. What we are getting? If alpha equal to 60, where the T1 comes to the on state, we add plus 30. That is from 90 to, what is the conduction of each SCR? 120 degrees. 90 to 210. Where is the T2? 210 to 330. T3 330 to 450. Similarly 0 to 90. Zero to 330. But observe here. Here you have V0 is equals to VA0. V0 is equals to VB0. V0 is equals to VC0. But observe here, from 0 to 90 actual conduction of T3, but if you go through this source, Yes. If you go through the source, zero to 90 na, 0 to 90 you have the output voltage Vc naught. But observe here, only 0 to 60 you have the positive source voltage. After that 60, negative voltage is available across the T3. Hence when T3 goes to the reverse biasing, then output voltage waveform will be observed. This is 60, this is 90, this is 180, here it is 210, it is 300, to 300, 330, like this. So 0 to 60 you have the output voltage, no problem. But 60 to 90, T3 is in reverse bias, so output voltage is 0. And from 90 to, so you rewrite here 0 to 60. Similarly, T1 where on? T1 90 to 210. Observe here, 90 to 210. You follow the VA naught na? 90, this one. 60 to 90 output voltage is 0, but 90 to 210 up to 180 you have the positive portion of the VA naught. Hence why that portion is available across the load, no problem. But 180 to 210, again you have the negative pulse. Hence why 180 to 210 there is no output voltage. And again here you rewrite this one is up to 180 only. 90 to 180. Similarly here also 210 to 300, 330 to 420. Then output voltage waveform will becomes like this. Output voltage waveform 210 to 300 and next this one. So here it is the conduction of T3, it is the conduction of T1, T2, T3. So what you will observe here, from this three-phase half-wave converter, if alpha less than 30 degrees, then we are getting the continuous conduction mode under R load. Three-phase half-wave converter with R load, if you have alpha less than 30 degrees, we are getting the continuous conduction mode, and if alpha greater than 30 degrees, then we are getting the discontinuous conduction mode. Then we are getting the discontinuous conduction mode. See here, alpha less than 30, continuous, always you have some current in the output. Alpha greater than 30, here I am taking 60 degrees now, hence why in this portion the output current is 0, here also output current is 0, here also output current is 0. If the load current is 0, then we are getting the discontinuous conduction mode. It's very, very important. If you go through this three-phase half-wave converter, depends upon the firing angle, we are able to operate in two modes with R load only. If alpha less than 30 degrees, we are getting the continuous conduction mode, and if alpha greater than 30 degrees, we are getting the discontinuous conduction mode. We are getting the discontinuous conduction mode. Next, average DC output voltage. Here I just want to find out the average DC output voltage. First case, alpha less than 30 degrees, like continuous conduction mode. So what is the average DC output voltage? V naught is equals to how many pulses you are generating for completion of one full cycle? 3 pulses. So 3 by 2 pi integral, what is the duration of each pulse? See, if you take alpha equal to 0, what is the duration of the pulse? 30 to 150. If you take alpha equal to 30, 60 to 180. So we will write these limitations are from 30 plus alpha to 120 plus alpha. 30 plus alpha to 120 plus alpha. How much you transfer? Phase voltage Vmp sin omega t d omega t. So by simplifying this expression, what you are getting? 3 Vmp by 2 pi integral sin omega t is minus cos omega t between the limits 30 plus alpha to 120 plus alpha. So by simplifying this expression, 3 Vmp by 2 pi minus cos 120 plus alpha plus cos 30 plus alpha. 3 Vmp by 2 pi minus cos 180 minus 30 plus alpha to 120 plus 150. Why? Because if you take alpha equal to 0 na, T1 conducts for 30 to 150. If you take alpha equal to 30, 30 plus 30, 60 to 180. Hence why we will take the limitations like 30 to 150 plus alpha. So here also 150 plus alpha. So minus cos 150 plus alpha. So we will write cos 180 minus 30 minus alpha plus cos 30 plus alpha. So cos 180 minus 30 is 150 minus of minus plus alpha. So cos 180 minus theta minus cos theta, you replace here, what you are getting? V naught is equals to 3 Vmp by 2 pi between the limits, minus of minus plus na, so cos 30 minus alpha plus cos 30 plus alpha. So what you are getting? Cos of a minus b plus cos of a plus b, 2 cos a cos b. So finally V naught is equals to 3 Vmp by 2 pi 2 cos a cos b, cos 30 cos alpha. What is cos 30? 1 by 2. Cos 30 is root 3 by 2. So substitute that value, 3 root 3, 2 gets cancelled. This one. Cos 30 is root 3 by 2. So 3 root 3 by 2 into pi Vmp cos alpha. That is the average DC output voltage of 3-phase half wave controlled converter with R load in continuous conduction mode. V naught is equal to 3 root 3 Vmp by 2 pi into cos alpha. Second case, alpha greater than 30 degrees, then you are getting the discontinuous conduction mode. Then the average DC output voltage is V naught is equals to, for completion of one full cycle we are getting the 3 pulses. So 3 by 2 pi integral 30 plus alpha to 180 Vmp sin omega t d omega t. Why we will take 180 means, observing the output voltage waveform. For alpha equal to 30, 60 to 180, no problem. For alpha equal to 60, 90 to 180, If you vary the firing angle, corresponding that if you choose alpha equal to 30, 30 plus 30, 60 to 180. If alpha equal to 60, 60 plus 30, 90 to 180. If you choose alpha equal to 90 na, 120 to 180. So ending portion is 180. Why? Because after that 180, negative source will be available across the thyristors. Hence why the maximum limitation is 180 and the minimum is 30 plus alpha. So what we will simplify? By simplifying this expression, V naught is equals to 3 Vmp by 2 pi minus cos omega t between the limits 30 plus alpha to 180. By replacing this, V naught is equals to 3 Vmp by 2 pi cos 180 is minus 1 minus of minus plus cos 30 plus alpha. So here it is the average DC output voltage of 3-phase half wave control converter with R load in discontinuous conduction mode. So in this class we just discussed the single phase, we will revise the single phase converters and we concentrate on 3-phase half wave converters with R load for alpha less than 30 degrees and alpha greater than 30 degrees. We will consider the output voltage, output current. If you go through the output current waveform, here we have the resistive load now. Output current is simply in phase with the voltage. And we also derive the average DC output voltages both in case of continuous conduction mode and discontinuous conduction mode. Thank you.